So our goal today is to kind of unpack that journey from maybe some early, really ambitious ideas about materials to the complex stuff we see now. We'll be drawing on sources like Melissa Schilling's work on managing innovation.
Yeah, her book's got a great case study if we can start with.
Exactly. Let's jump right in with that. Magna International's carbon fiber lightweighting project. Schilling features it early on, and it seems like a perfect way to see the real-world challenges and pivots when new tech meets mass production. Okay, let's unpack this one.
Okay, so around 2017, Magna set this, incredibly ambitious goal. They wanted to develop a carbon fiber subframe.
A subframe, that's a pretty critical part.
Huge structural part, and not just develop it, but make it suitable for high volume production.
Really?
We're talking 150,000 units a year.
Wow, okay, that's mass market territory.
Definitely. And carbon fiber, reinforced polymers, CFRP, the strength to weight ratio is just fantastic.
Correct.
Way beyond steel, even aluminum.
And Magna knew this stuff already, right? They weren't totally new.
No, they weren't strangers to CFRP. They'd done smaller scale things like hood panels for Cadillac. Components,
Right, but a whole subframe and that kind of volume, that sounds like a different beast entirely.
Exactly. And that's where it got tricky. Scaling up to something that complex, that structural for mass production, it just threw up some major hurdles.
Like what specifically? What were the roadblocks?
Well, first off, the cycle times. Part to part, it was just slow, way too slow for that kind of volume. Then the processing itself was incredibly complex.
Right.
And CFRP has these unique failure modes that can be hard to predict compared to metals. Plus, they had this really tough cost target. Get this, $20 per pound of weight removed.
$20 a pound? That sounds tight.
Very tight. So this whole project, ambitious as it was, it really drove home a key lesson for the industry. Relying on just one material, even a super advanced one like carbon fiber, well, it often hits a wall when you try to scale it for mass market cars.
A practical wall and an economic one, too.
Sounds so. Precisely. It wasn't just about finding the one miracle material anymore.
Okay, so that initial dream, the single revolutionary material, it bumped up against reality. So what happened next? How did the industry pivot strategically to keep pushing lightweighting forward, especially, with electric vehicles really taking off?
Yeah, that's the key driver, isn't it?
Because for EVs, it's not just fuel efficiency anymore, is it? It's range.
Exactly right. That initial experience combined with the EV boom, it forced a fundamental shift. Everyone realized, okay, lightweighting an EV directly boosts battery range.
Which is the golden metric for EVs.
Absolutely. Or you could use a slightly smaller, lighter battery pack for the same range, which also saves cost and weight. And it lowers the overall environmental footprint too. So yeah, the industry moved away from chasing that single miracle material.
Towards what then?
Towards a much more multifaceted strategy, leveraging a whole suite of advanced materials, not just pinning hopes on one.
Okay, so the carbon fiber dream didn't die, but it sort of shared the stage. This new reality, this multi-material approach, what does it actually look like? What materials are we talking about? I guess I assume steel was kind of old news in lightweighting.
Yeah, that's a common thought, but steel is far from done. We've seen huge leaps, particularly with what they call third-generation advanced high-strength steels, AHSS.
With HSS.
These new steels, they offer amazing strength, but also better formability, so you can design parts that are thinner, lighter, but still meet all the critical crash safety requirements.
So you use less steel, basically, but it's smarter steel.
Exactly. It makes steel a really cost-effective, practical lightweighting tool, especially for mass production. Shows how even traditional materials can, reinvent themselves.
That's really interesting. Innovation where you might not expect it. What about aluminum? We hear a lot about aluminum bodies, things like that.
Yeah, aluminum's become a real workhorse, and it's scalable now. Great strength to weight, obviously. Excellent corrosion resistance, too. And maybe critically, it's highly recyclable.
The big plus these days.
Huge. And for EVs specifically, it's increasingly the go-to material for battery enclosures. That directly helps with range, like we said, and also safety. Containing the battery securely is paramount.
Right, makes sense. So, okay, we've got advanced steel, we've got aluminum playing a big role. Carbon fiber is still there for high-end stuff. What about other composites? Where do they fit in?
Well, like you said, carbon fiber is still key for, the super high-performance applications, luxury sports cars, that kind of thing. But the industry's gotten smarter, more strategic about using different composites.
Oh.
Like glass fiber reinforced plastics, GFRP. They're getting a lot of traction for things like, again, EV battery cases or covals. They offer a really good balance between performance and cost-effectiveness.
Better cost than carbon fiber, presumably.
Oh, significantly. But the biggest shift, the real game changer, is the embrace of what we call multi-material design strategies.
Multi-material design. Okay, tell us more about that. That sounds like where the real strategic thinking comes in.
It absolutely is. The industry basically realized, look, a single material just isn't the best answer for something as complex as a whole vehicle. Modern cars are now these sophisticated patchworks, really, intelligently combining AHSS, aluminum, various composites.
So using the right material in the right place.
Precisely. Leveraging each material's unique strength, weight, stiffness, cost, formability for optimal overall performance, safety, and, of course, weight. Think about cars like the BMW i8 or the Audi A8. They're showcases of this kind of intelligent blend.
Not just one dominant material.
Right. It's a fundamental shift in design philosophy, moving away from finding the best material overall to finding the best fit material for this specific function. It's like conducting an orchestra rather than just playing one instrument really well.
That's a great analogy, an orchestra. But conducting an orchestra like that with all these different materials, that must create its own challenges, right?
Yeah.
Beyond just choosing the materials. How do you integrate it all? Where do the headaches happen?
Yeah, you definitely need the right manufacturing and joining processes to make that orchestra play in tune. These material advances really rely on innovations on the factory floor, like additive manufacturing or 3D printing.
3D printing cars, or parts of them at least.
Parts, exactly.
Oh.
It's unlocked incredible design freedom. You can create these really intricate, lightweight structures using techniques like topology optimization or lattice designs.
Topology optimization. That's where the computer figures out where material isn't needed, right?
Basically, yes. Think of designing like nature does, like a bone structure. Material only exists where it's needed for strength. You get these incredibly efficient, lightweight, often complex-looking parts.
And I suppose you can combine parts too, make one printed part do the job of several older ones.
Exactly. Consolidating components, reducing complexity, reducing fasteners, all saves weight and assembly time.
That's fascinating. So the parts themselves are designed differently.
Okay.
But then you have, say, an advanced steel part next to an aluminum one, next to a composite piece. How do you actually stick them together reliably, especially for mass production?
That's the other crucial piece, advanced joining technologies. With such diverse materials coming together, you need new ways to join them. You can't always just weld everything like in the old days.
Right. Dissimilar materials don't always play nice.
Precisely. So we're seeing huge innovation in welding techniques for new alloys, but also in adhesive bonding using structural glues and advanced mechanical fastening, like self-piercing rivets or flow drill screws.
So new glues, new rivets, basically.
Sophisticated versions, yes. They overcome those compatibility issues, create really robust bonds, and sometimes even eliminate traditional fasteners altogether. These aren't just making connections stronger, they're cutting complexity, weight, and assembly time. Huge for efficiency.
And crucial for things like battery modules or EV motor housings, I imagine.
Absolutely critical for those EV systems, where you have different materials needing to work together perfectly.
It really sounds like lightweighting isn't just about the car's body or frame anymore. It's penetrating deeper into the actual systems of the car.
It absolutely is. Lightweighting now definitely extends to functional systems. For EVs, think about thermal management. Designing compact, efficient cooling modules for the batteries, the motors, the power electronics, that's critical.
Lighter cooling systems save weight too.
They do, and they directly impact the EV's range and performance by keeping everything at its optimal temperature efficiently. It's become a truly holistic approach, not just the structure, but everything.
And to pull all this off, this multi-material system-wide integration, I imagine organizations themselves had to change how they were structured, how they made decisions.
Exactly. You hit on a key point. Achieving this level of integration meant rethinking internal structures and processes. The lightweighting revolution, it turns out, isn't just about material science and engineering. It's equally about optimizing the organizational intelligence to actually leverage those materials strategically.
Okay, so it loops back to the organization itself. The source material, Schilling's book, mentions Magna's team for that initial carbon fiber project was a heavyweight team. What does that actually mean organizationally? And what are the sort of pros and cons?
Right, a heavyweight team. In organizational terms, like Magna's team led by Tom Pilette, it typically means you have a dedicated project manager, someone like Pilette, with real authority.
Clout, basically.
Yeah, clout. And the core team members are usually full-time on the project, pulled from different functional departments, materials, manufacturing, design, etc. The sheer complexity and strategic importance of figuring out scalable carbon fiber really demanded that kind of setup.
Makes sense. So the strengths seem obvious.
Yeah, the strengths are pretty clear. You get strong leadership and focus because the project manager has authority. Pilette's role showed high commitment from Magna. It fosters excellent cross-functional integration. You've got all the key expertise sitting together, focused on the same goal.
Better communication, presumably.
Much better communication and faster problem solving, which was vital for hitting those tough targets like that 3-minute cycle time they were aiming for. And of course, clear accountability. The team owns the success or failure.
Okay, sounds good. But I'm guessing there are downsides, even with a strong, dedicated team like that. Potential blind spots.
Oh, definitely. No structure is perfect. One potential issue is isolation. The team can become a bit of an island, separated from the rest of the organization.
So knowledge doesn't flow back easily.
Exactly. Transferring that knowledge back into the functional departments after the project can be a challenge. Also, these teams often have to work within the constraints of existing vehicle platforms or architectures. That can limit really radical, clean sheet thinking sometimes.
They're optimizing within boundaries, maybe.
Kind of. And there's always the risk of the not invented here syndrome. Other departments might feel less ownership or be resistant to the outputs. Plus, let's be honest, heavyweight teams require a significant resource commitment. Pulling key people full-time isn't cheap.
Right. Big investment. Now, thinking about the auto industry today, supply chains are incredibly global. How would distributed teams factor into this? When you're trying to do complex innovation, but your team members are spread out geographically.
That's a huge factor now. While the source didn't detail Magna's team locations specifically, generally speaking, having teams spread out geographically has its pluses. You can access diverse talent pools, maybe be closer to key suppliers like Zoltech or Toray for carbon fiber in Magna's case, or major customers like BMW.
Follow the sun development, maybe.
You can even enable a near 24/7 work cycle across time zones sometimes, and you get valuable local market insights.
Okay, but the challenges must be significant too. Trying to collaborate across oceans and time zones.
Oh, absolutely. The informal knowledge sharing, the water cooler chats, that's much harder. You risk creating information silos. Time zone differences, obviously, can delay decisions. Cultural differences can lead to misunderstandings if not managed carefully.
And just building trust, maybe?
Yeah, that lack of face-to-face interaction can definitely hinder trust building and sometimes stifle those spontaneous innovative sparks. And then there's managing the complex global supply chains themselves, especially when dealing with new materials where there might be, supply chain capacity concerns. It adds layers of logistical complexity.
It sounds easy to say global team, but making it actually work effectively sounds tough.
It is tough. Getting everyone truly on the same page, literally and figuratively, requires effort.
So how have modern communication tools changed that? All the tech we have now, has it really bridged those gaps for complex innovation?
It's made a massive difference, honestly. It's mitigated many of those challenges. Think about knowledge transfer. We now have robust video conferencing, shared document platforms, collaborative project management tools, digital whiteboards. Real-time interaction is possible in ways it just wasn't before.
So less waiting for emails across time zones.
Exactly. Decision-making gets streamlined with instant messaging, quick polls, digital voting tools within meetings. And for innovation itself, virtual whiteboards, cloud-based CAD collaboration, even things like augmented and virtual reality for design reviews or virtual factory tours.
VR factory tours, wow.
Yeah, it helps create a sense of shared presence, fosters some of that spontaneous interaction that's so crucial for innovation. It's getting closer to mimicking the benefits of being in the same room.
That's a significant shift. Now, drilling down into team dynamics again, the notes mentioned Tom Paulette used a voting approach for decisions within his heavyweight team. Can we look critically at using voting, just generally, in new product development, especially for really innovative stuff? How does it stack up against other ways of making decisions?
Okay, yeah, a general voting approach, usually meaning majority rule. The upside is it can be efficient, especially for more straightforward decisions. Everyone gets a formal say, and you get a clear outcome. Quick, democratic on the surface.
There's always a but.
There is. The big cons are pretty significant. First, the minority voice. Those who voted against the decision might feel disengaged, less committed to implementing it.
Right, they lost the vote.
And you might actually lose valuable insights. What if that minority opinion held the key to avoiding a problem down the line? Voting can sometimes suppress dissent or critical analysis because the focus shifts to just getting enough votes.
Risk of groupthink, too.
Definitely a risk of groupthink. And in really complex innovation, where the best path forward might be non-obvious or even unpopular initially, a simple majority vote could easily sideline a truly revolutionary idea.
So what are the alternatives then, if voting isn't always ideal for innovation?
Well, you've got consensus-based decision-making. Everyone has to agree. The huge pro is high commitment and often richer solutions because you've explored every angle to get everyone on board.
But I imagine that takes forever.
It can be incredibly slow, yes,
Yeah.
and prone to deadlock if you just can't get everyone to agree. Then there's the opposite. Authoritative or hierarchical decision-making. The leader decides.
Fast and clear.
Very fast,
Yeah.
clear accountability. But the big risk is lower team buy-in. And if the leader doesn't have all the information or overlooks something important, you can make poor decisions.
So for complex stuff, maybe something in between.
Often, yes. A blended approach. Maybe something consultative where the leader actively seeks input and discusses options with the team but ultimately makes the final call. That can balance speed with buy-in and diverse perspectives. The best approach often depends on the specific decision and the team context.
Right, so the one size fits all. So, okay, bringing this all together now, we've gone from Magna's early carbon fiber goals and the hurdles they hit through this whole multi-material revolution, advanced manufacturing, new ways of working. What's the big picture takeaway for you, the listener, trying to navigate maybe your own complex projects?
Well, I think the core story here is how lightweighting itself transformed. It started as, focusing on specific parts, mostly to save fuel. Now, it's become this holistic, system-wide imperative. It's absolutely fundamental to the future of mobility.
Underpinning EVs, you mean?
Underpinning EVs by extending range, enabling safer autonomous driving systems because lighter cars are easier to control, and pushing sustainability through recyclability and exploring new, greener materials. It's really a story of continuous innovation driven by constantly changing demands.
It's been quite a journey we've covered. From those initial carbon fiber challenges to the strategic pivot towards multi-material design using those advanced steels, aluminum, GFRP, alongside carbon fiber. We touched on the crucial enabling tech, like additive manufacturing and those advanced joining methods.
And the thermal management piece, too.
Right, and how thermal management for EVs is now part of that whole lightweighting puzzle.
Yeah.
And importantly, how the organization had to adapt the team structures, the decision-making needed to actually deliver on all this complexity. It's not just the tech, but how you organize around it.
Exactly. The human element, the organizational design is just as critical.
So here's a thought to leave you with. Considering how vital this multi-material design and integrated systems approach everything from the structure to the EV thermal systems, how vital that is now in automotive, how might those principles we talked about, fostering experimentation, using adaptive decision-making, how might they apply to complex challenges and innovative projects in your field, especially if you're dealing with fast-moving tech and maybe diverse distributed teams?
Yeah, it's fascinating, isn't it? Because this continuous journey towards lighter, smarter, more sustainable vehicles, it isn't just about material science or engineering breakthroughs. Fundamentally, it's about how organizations structure themselves, how they manage knowledge, how they make decisions to keep that relentless innovation going, especially when facing complexity and, as we saw with Magna, unique failure modes. It really feels like a blueprint for adaptability, relevant way beyond just cars.